Hey guys, this is Mr. Post, and on today's video we'll be checking out solubility curves. It's a way for us to express how temperature affects solubility, but to actually put it on a graph. So we're going to be keying in on temperature today, and its effects on how things dissolve, and we'll be expressing our information on a curve, which is kind of a graph. Let's get into it. Before we get into this whole entire topic, we do want to go over a couple key terms. The first key term we want to get into is saturation. What does it mean when something is saturated? And this simply describes a solution that has the maximum amount of solute dissolved. The maximum amount of solute that has been dissolved. A good analogy for this would be like a paper towel that is soaking wet. The paper towel can no longer absorb any more water, therefore it's saturated with water. Another way you can think of it as if you're making like an iced tea mix, and you're adding like iced tea to a glass of water, the point at which it no longer dissolves and actually starts to accumulate on the bottom of the glass, that is the point at which the solution is saturated. Now reverse, on the other side, you're going to see a solution that is unsaturated. That's the point at which you can actually continue to dissolve more of that substance. You have not reached the maximum dissolving point yet. When you're making that iced tea, a good way to look at it would be to say, I can continue to dissolve more sugar into my iced tea mix. You know what? Your solution is not saturated yet. You are unsaturated. Another example, let's use a paper towel analogy. If you have a paper towel that's dry, it is totally unsaturated, meaning you have a lot less than the maximum amount of water that paper towel can absorb. Even a paper towel that is damp or even sort of wet, it is not 100% saturated, and if it can still absorb some more water. A term you're probably unfamiliar with, though, is supersaturated. And that's not a term we're going to go crazy on. We're going to hold back. We're not going to go nuts on this one, but we're going to simply describe a solution that has more than a saturated solution has. You're dissolving more solute than you really should at that given temperature. Okay? And that is known as a supersaturated solution. This is a solubility curve. It has three regions, and it has those terms we've just defined. The key thing you're going to see on this line is this graph. Okay, this line that goes right down this graph. This is the curve. All right, so we're looking for a solubility curve. This is a curved line, and that's my solubility curve. The line represents the point of a temperature and solute that is a saturated solution. So any point on this line are the conditions for a solution to be saturated. Now let's check out the axes here. On the x-axis you have temperature. So we're dealing with temperature today and heat. Over here, solute is how much of a substance dissolves. So once again, this curve is nothing more than points. Let's say at this given temperature, how much solute can I dissolve? And you go over to this line over here. At this given temperature right here, let me go up to this line right here. Okay, at this point, I can dissolve this much in that solution. Okay, it'll become a little bit more clear as we go on through this lesson here. The whole zone underneath this graph, underneath this line here, is an unsaturated solution. So if I said, what is this point right here? Well, at that given temperature and at that given amount of solute dissolved, that would be an unsaturated solution. The whole zone above our curve, let's just say I picked this point right here. Well, that temperature going down there, I can dissolve that much. If my solution had those conditions, it would be a supersaturated condition. And likewise, if I have any point on this line here, they would be considered saturated solutions. It should all make sense as we go through the lesson, though.
Solubility curves are graphs that show the amount of solute, usually in grams, that will dissolve in a specific amount of water, usually 100 grams, at various temperatures. So let's take a look at a solubility curve. Here's one. In fact, the one that's on your worksheet will look a lot like this. I think it's identical. If not, it's really similar. So let's take notice of the x and y axis first. Notice that the x-axis is your temperature, your various temperatures. Your y-axis says grams of solute per 100 grams of water. That's pretty common, pretty traditional for what we see. If we wanted to know how many grams of solute would dissolve in 1,000 grams of water at a given temperature, we would simply use the same chart, the same solubility curve or graph, and multiply whatever mass we read off of this gram times 10, because it would if 100 grams dissolves 10 grams of a solute, then 1,000 grams of water or a liter of water would dissolve 10 times as much, or 100 grams of the solute. The next thing to notice that just about every curve on this graph, potassium chlorate, sodium chloride, potassium chloride, ammonium chloride, potassium nitrate, sodium nitrate, potassium iodide, all have a slope in this general direction, which is a direct relationship, meaning that as temperature increases, solubility increases, the amount of solid that we can dissolve. We know that. We talked about that. That's our iced tea and sugar example, that if we heat up the iced tea, we can dissolve more sugar in it. Well, let's also notice, as I erase some of this, that there are two curves that I didn't circle on this graph. One of those curves is the substance NH3. Do you remember what NH3 is? NH3 is ammonia, because we talked about how gas solubility decreases with temperature. We see some kind of curve like that. So as temperature increases, solubility decreases, and we call that an indirect relationship. So solids have direct relationships, gases have indirect relationships. You might want to write that down. That's good to know. So how are we going to use this graph? Well, I actually have a whole worksheet related to a solubility curve.
Now we're going to look at some examples of problems that can be solved using the solubility curve. I'll try to do at least one of each type of problem in order for you to get comfortable with them. The first thing you need to be able to do is look at a point on the graph and decide whether it makes a saturated, unsaturated, or supersaturated solution. So for this problem here, we have 80 grams of sodium nitrate at 30 degrees. Which would put it right here on my graph. The curve for sodium nitrate is here, so this is a point below the line, meaning that it's an unsaturated solution. We could fit more in there. Our next example is looking at 80 grams of potassium chlorate at 50 degrees. This point here on my graph. The curve for potassium chlorate is down here, so we have more than a saturated solution, or a supersaturated solution. And the last question is looking at 30 grams of potassium chloride at 10 degrees, right there on my graph. And it appears to be right on the line for potassium chloride, making this a saturated solution. So they want to know how many grams of potassium nitrate we can fit in 100 grams of water at 60 degrees Celsius. So I go to 60 degrees Celsius and I'm going to go up until I hit the line for potassium nitrate, right around here. So at 60 degrees I can fit about 107 grams of potassium nitrate in a saturated solution. So we want to dissolve 65 grams of potassium nitrate and 100 grams of water. So I've got 65 grams and I'm going to trace it over until I hit potassium nitrate. Right around here. I go down and it looks like it's a little over 40 degrees. So we'll say 41 degrees Celsius. So we've got 75 grams of sodium nitrate at 35 degrees, looking at a point here on my graph. A saturated solution at this temperature can hold this amount. So to figure out how much more I can add, I simply subtract the two numbers. So 100 minus 75, I can fit an additional 25 grams in before I reach a saturated solution at this temperature. So we've got a saturated solution of sodium nitrate at 30 degrees Celsius, which would put me here on my graph, and we've got a saturated solution at 60 degrees. So if I want to know how much more can be added, I simply subtract the two numbers, leaving me with about 30 more grams that can be dissolved at this higher temperature. So we've got a saturated solution of potassium chloride at 70 degrees, putting me here. And if I cool it down to 25 degrees, I should not be able to fit as much in there. In fact, I can only fit this amount. If the solution is agitated, this extra solute will precipitate out of solution. So the difference between these two will come out of solution. So 20 grams will fall out. So if I add 20 grams of potassium chlorate at 40 degrees, I'm looking at a point here. A saturated solution for potassium chlorate is here. So even though I added 20 grams, it doesn't mean that it'll all dissolve. At 40 degrees, the maximum I can fit in there is 17 grams. So 17 grams will dissolve, but the 3 grams remaining will not. If you notice, this problem is different than the others because it's not talking about 100 grams of water, it's talking about 50 grams of water. So we can still solve this problem, but our graph is only good for 100 grams of water, so we're going to have to figure out what it would be for 100 and then alter it for the different amount of solvent. So with 100 grams of water at 50 degrees, I can fit about 84 grams. So in 100 grams of water, I can fit 84 grams of the solute. We're going to set up a ratio and make it 50 grams of water instead. So 84 over 100 equals x over 50. When we cross multiply, we find that we can only fit 42 grams of the potassium nitrate. So you got to be careful. If a problem does not mention 100 grams of water, you may have to alter your response.